Okay, in this video I'm going to do an example problem on latency. And latency is the total amount of time that it takes to send a frame from point A to point B on a network. And we're going to see here an example where we calculate the total time needed to send a frame a distance of 100 meters at a data rate of 1 megabit per second. And we're going to calculate the latency as the propagation time plus the transmission time. Okay, propagation time is simply the speed of the wave on the transmission medium, and transmission time is calculated using the length of the frame and the bit rate, which is here 1 megabit per second. What we'll do is we'll compare the propagation time and the transmission time in the end, and I'll have some more comments on that. We can draw this. Let me start out by saying let's get our frame from point A to point B, and let's make the time axis go vertically downwards, and let's suppose that it takes a certain amount of time for A just to get those bits out onto the medium. And what I've done here is I've taken the first bit. Here's the first bit. And the first bit is going to propagate from point A to point B. And in time, that first bit sort of went out across the line like that. And so as time goes down, as time progresses, the bit moves from A to B. The second bit on the line follows closely behind the first one. And finally, the whole entire frame sort of propagates across that wire, and you can see here that when B finally receives the entire frame, okay, at some time. And what we've got here is we've got our propagation time, which is the time it takes that first bit to get from A to B. And we've also got our transmission time, which is the time needed to put the bits on the wire. And I'm afraid I drew them to be almost equal here. But in general, we're going to see that there may be a large disparity between these two amounts of time. Okay. In any case, so I've drawn here the propagation time for that first bit, and then the transmission time is the time that it takes either for B to receive the whole frame, starting from the time it receives the first bit all the way down to the time it receives the last bit. The transmission time is also the time it takes A to put the whole frame out on the wire, starting with the first bit to the time it emits the last bit. Okay? And so here, let's do the calculation. We're given 200 meters per microsecond for our propagation speed. I'm going to use V for that. And I'm going to convert this into meters per second by saying that they're 10 to the 6th microseconds in 1 second. And we're going to see we get 200 e to the 6th. And now we've got microseconds canceling, and I get meters per second. And you'll recognize this as 2/3 the speed of light. Speed of light, c, is 3 times 10 to the 8th. And so this is 2, if I write it, 2e to the 8th meters per second. So I took the 100 and added 2 to the 6th. So I got 2 to the 8th to the 8th. So this is 2/3 the speed of light. This is, by coincidence, pretty much the speed of voltage pulses on a wire and pretty much the speed of optical pulses in an optical fiber. Okay? The propagation time to go a distance of 100 meters on this wire, I'm going to let d be the distance on the wire, and I'm going to write that down as 100 meters. And we're going to say that the propagation speed is the propagation distance divided by the time it takes. So I'll call that t prop. And when I solve for t prop, I get distance divided by v. And now you see I'm following my good problem solving practices by writing out the whole equation, making sure I've got all the variables labeled with numbers, with units, and I can finally plug in 100 meters over 2 times 10 to the 8th meters per second. And my meters are going to cancel out, and my seconds are going to come up to the numerator to give me a time. And this is either 50, 100 divided by 2 is 50 e to the 8th, 50 e to the minus 8th when I bring that up, or 0.5 e to the minus 6 seconds, which is 0.5 microseconds. And make sure you can either get through this calculation in your head the way I just did, or use a calculator to do it. So half of a microsecond to get from point A to point B on the wire. Now we're going to calculate transmission time. And now we've got a very similar equation to our velocity equation here, but instead we have a bit rate. For our rate, we have the number of bits in the frame instead of distance, and we have T trans instead of T prop. Solving this for T trans, we get the number of bits in the frame divided by the bit rate, and we have all of those. The bit rate, RB, is 1 megabit per second. Let me straighten that out a little bit. 1 megabit per second. And I'm going to plug those numbers in now. So again, I'm following good problem solving practice. And, well, I'm not until I write NB is equal to 1500 bits. Let me straighten that one out too. Okay, so I get 1500 bits divided by 1 e to the 6th megabit per second. Or nope. Boy, I've got to erase over and over on this one. Bit per second, and I'm going to get a time. I'm going to get 1500 microseconds. And it's 1500 divided by 1, and then e to the 6 becomes e to the minus 6 seconds, and so I'm going to call that a microsecond. And so the total time is T prop plus T trans, which is 0.5 microseconds plus 1500 microseconds, which is 1500.5 microseconds. So T trans totally dominates, okay, by a factor of about 3,000, as a matter of fact here. And so for the final comment here, I'll say that if we were to increase our bit rate by a factor of 1,000 and go to 1 gigabit per second, then our T trans, I'd have a 1 e to the 9th in the bottom here, in the denominator here, this equation, and I get 1500 e to the minus 9, which is 1.5 microseconds. And so if I had 1 gigabit per second, I'd have T trans is 1.5 microseconds. And then, so you can see that when we get to gigabit speeds, the propagation times and the transmission times become comparable. Whereas when we're down at a megabit speeds, transmission times are much larger than propagation times. Okay, hope this helps on this one. Thanks for listening.